All right, so this is 5.1, Law of Sines. And we're going to talk about, obviously, the law of sines. And we're going to spend most of our time using it in the context of solving triangles. So our strategy is, and we'll have one kind of application for it, which revisits some of the word problems from the past. So our strategy is going to be, first, we're going to introduce the law of sines. We're going to justify it, tell you where it comes from. And then we're going to talk about the general idea of solving triangles. There's some kind of general mathematical principles or philosophies behind the ideas. And then we'll actually do some solving of triangles, at least the triangles we can solve using the law of sines. So what's going to happen is the other section, 5.2 this week, is going to be the law of cosines. And the situations we can't deal with the law of sines are going to be covered by the law of cosines in terms of solving triangles. So after 5.1 and 5.2, we'll have kind of a complete picture of how to solve triangles. All right, that's how we're using the law of sines and cosines this week for our class. But for example, the law of cosines will pop up in the future. And it's actually really, really important in many ways. But our focus is solving triangles. Just to show you, just to kind of have an application for these guys that's very approachable. Okay, so what is the law of sines? Let me just introduce our notation for 5.1 and 5.2. So in 5.1 and 5.2, we are talking about general triangles. So it contrasts this to Math 92, where Math 92 was only right triangles. This is any triangle, all right? Doesn't have to be a right triangle. So a general triangle, we're going to denote in these two sections using side lengths A, B, and C. So maybe A, B, and C, all right? It doesn't matter which side I label which, as long as one of them is A, one of them is B, one of them is C. And then we're going to denote the angles using Greek letters. And they're going to correspond, the names of the Greek letters are going to correspond to the side that's opposite to that angle. So we have A here is this length. And so the angle opposite to it, I'm going to call it alpha, right? The Greek A. B is here. So the side opposite to it, I'm going to call it beta. All right, the Greek B. And then C, the opposite side, is going to be gamma, which is the Greek C. All right. Okay, so we're going to be using this notation for both 5.1 and 5.2. And again, the ordering of this A, B, and C doesn't matter as long as the opposite side and angles are consistent. Right. What I mean by ordering is I decided to call this one A, this one A, that one B, and that one C. If I had called this one B, that one A, and that one C, same, everything we talk about still applies. All right. Okay. So given a setup like this, the law of sines says that sine of alpha, so sine of this angle right there, over A, right? So alpha and A. So it's always the angle and then the side opposite to it. The ratio of those two numbers is equal to sine of beta over B, and that's also equal to sine of gamma over C. Right? So all these three quantities are equal. Okay. Notice that all these kind of, in a way, make sense. Alpha is an angle, but once you take sine of it, you get a number, right? And then you're dividing a number by a number, so everything makes sense, right? If for whatever reason you had kind of, in a way, an angle over a length or something like that, then it would be probably something weird, all right? So you're probably doing something incorrect in that situation. Okay, in any case, this is the law of sines. All right, or also called sometimes just a sine law or sine laws. Why plural? Well, because there's actually this one expression here contains two actual equalities, right? Sine of alpha over A equals sine of beta over B, and sine of beta over B equals sine of gamma over C. All right. Notice it's only two, because if I put these two, it's only two kind of new equalities that we didn't know before. And it's not three, because if you put these two together, because sine alpha over A is sine beta over B, and because sine beta over B is equal to sine gamma over C, that tells you that sine alpha over A is equal to sine gamma over C as a result of the first two. All right. So while it looks like there's in a way three equalities, there's actually only two. Right? There's only two new ones. That'll be important when we start discussing kind of the philosophy behind solving triangles. Okay. So this equality, or this kind of sequence of equalities, is always true for any triangle. Does not have to be a right triangle. All right. And we're going to be using it to solve triangles, at least for our class. Before we do that, let's explain why this set of equalities is true. And we're going to do that doing a general picture. So let's say something like this. Let me call this side alpha. Let me call this side, call this beta. Actually, let me be at least consistent with my picture up there. Actually, no, let me do this just to emphasize that it doesn't matter, right? As long as it doesn't matter which one alpha is, which one beta is, which one gamma is, as long as my sides opposite have the correct names. Okay. All right. So let's do this triangle here. I'm not going to need gamma and C for this discussion right here. Okay. So what I want to show is true. So I want to verify that sine of alpha over A is equal to sine of beta over B. Okay. And what's going to happen is the ones involving gamma, sine gamma over C, you can show it in exactly the same way from a different point of view. I'll say a couple words about that at the end. All right. What I'm going to do is I'm going to drop this perpendicular down to here, like that. All right. If I do drop that perpendicular, I'm going to get two right triangles. This right triangle here on the left and this right triangle here on the right. All right. I want to do this. The idea behind dropping the right triangle makes sense because what I'm trying to verify involves sines, sine of alpha and sine of beta, right? And a good way in terms of triangles, when you're working with physical triangles, you would like to think of sines in terms of opposite over hypotenuse, right? But you can't talk about opposite over hypotenuse if you don't have a right triangle, right? Remember, we're working with just a general triangle. It doesn't have to be necessarily a right triangle. So when we start our problem, or when we start this discussion, this triangle that we started with is not a right triangle. So you can't even say opposite over hypotenuse, right? There is no hypotenuse, right? Because there's no right triangle. So dropping this perpendicular down makes sense because it creates a right triangle for me in order to use the idea of sine being opposite over hypotenuse. All right. So in fact, let me give this. I dropped this guy down. Let me call this length. Let me call it y. All right. So this y is from here all the way down to here. This side length right here. Okay, the dotted red line. All right. Like I said, the reason I did it is because now I can describe sine alpha in terms of a triangle, right? So opposite over hypotenuse. And if I look at the triangle on the left, opposite is y, hypotenuse is b, all right? And luckily enough for us, if we look at the triangle on the right, and if we look at sine of beta, that's equal to opposite over hypotenuse again, except hypotenuse this time is a, right? So opposite is still y over a. Okay. Now I'm just going to put these two together. The first one, I'm going to rewrite this as b sine of alpha is equal to y. The second one, I'm going to rewrite it as a sine of beta equals y. And so what I have is both of these guys are equal to y. And so both are equal to each other. And so b sine of alpha is equal to a sine of beta, right? And that's actually what we want, because all I have to do now is divide by b on both sides, right? Or in other words, throw the b to the right-hand side, and then divide by a on both sides, right? And so I get sine of alpha over a equals sine of beta over b. And that's exactly what I want. That's the law of sines that relates alpha and beta. Okay. So a very nice kind of explanation because it only involves one idea, right? Drop the perpendicular. And the dropping the perpendicular is kind of easy to remember or understand because we're talking about sines. And if you want to talk about the context of triangles, you would like to talk about opposite over hypotenuse. And so you need a right triangle. And that's what dropping the perpendicular does for you. Okay. All right. Now, of course, the actual full law of sines also involves gamma and beta and you know, gamma and all that. But how do we deal with that? Well, in the same picture, if I have c here and gamma there, what I could do instead is drop the perpendicular this way, right? And then that would relate, so this one I called beta, this one, I don't need alpha this time. This one will be b, right? If I drop the perpendicular this way, then I would have two right triangles again, this one here and that one there, right? And so they would give me the, right, looking at this kind of tiny, this right triangle on the left, I would have, sorry, this looks a little messy here. I would have sine of gamma is opposite over hypotenuse would be b, right? And opposite would be a different length this time. Maybe we call it x. And then sine of beta would be opposite over hypotenuse. This time would be c. And then when you put those together, you get exactly the second half of our law of sines. So this, this second half right there. All right. And again, we don't have to prove the last one because if, you know, if one thing is equal to a second thing is equal to a third thing, then the first thing is, of course, equal to the third thing. All right, so that justifies our law of sines. Now let's use it. Okay, so again, let me write down our law of sines. We always want to keep this guy in mind. How are we going to use it? Well, the idea is we can use it to solve triangles. So again, let me draw a picture. Alpha, beta, gamma, C, A, B. All right. So what do we mean by solve a triangle? So what we mean is we have a triangle. There's 6 pieces of information given any triangle, right? So a triangle consists of 6 pieces of information. All right. The sides, A, B, C, and the angles, alpha, beta, gamma. All right. So when we talk about solving triangles, what we mean is problems like I give you a certain number of these pieces of information, and you have to give me the rest of them, right? So for example, a typical problem might be I give you A equals 2, B equals 4, beta equals 30 degrees, right? And the question is, what are the rest of these 6 pieces of information, right? In particular, what is C, right? What is alpha? What is beta? Okay. So that's the typical idea. I give you some pieces of information about these triangles. You give me the rest of them. All right. Now, of course, there's a whole lot of different combinations of which ones I give you. In this example, I gave you 2 sides and an angle, right? I could give you 3 sides, I could give you 2 angles and a side, and so on. All right, so that's the kind of variations that you'll see in this type of problem. Okay, and again, once you've figured out the rest of this info, right? Once you figured out, for example, C, alpha, and beta, then you know everything you need to know about the triangle, right? Because the triangle only consists of 6 pieces of information. Okay, so let's talk about what are the pieces of information that we're going to be giving you for these sections, 5.1 and 5.2. Let's talk about a little bit about the philosophy of why we're giving you the information that we are giving you. And then we'll actually solve some triangles using the law of sines. And then in the next section, using the law of cosines. All right, so here's the idea. We're going to be giving you, in these sections, 3 pieces of information. So of the 6, we're going to give you 3. Maybe I draw the triangle again, just because it's been scrolled away. Beta, gamma, C, A, B. I'll talk about Y3 in just... Actually, let me talk about Y3 right now. So Y3. So the deal is, if we look at just this problem, this triangle here, there's 6 pieces of information, right? So you can think of this as 6 unknowns, in a way, right? Now, philosophically, or maybe not philosophically, this might not be the best word, but generically in math, if you have a certain number of unknowns, you would like to have the same number of equations relating those unknowns for there to be solutions, for there to actually be a finite number of solutions to those problems. All right. So in general, if you have more equations than unknowns, then there's going to be no solutions to your problem. In general, if you have more unknowns than equations, there's going to be an infinite number of solutions to your problem. And if you have exactly the same number of equations and unknowns, you expect there to be a finite number of solutions. All right, so this is a general math principle. It's not always true, so I'm very, very careful to say that generally, blah, blah, blah. All right, but it's a thing that's generically true. All right, so what that means in our context is we have, just at the start, right, just looking at this triangle, there's 6 unknowns, right? So in order to actually kind of determine a triangle, if I only give you, 4 equations or 4 relationships between those unknowns, then I'm going to have fewer equations/relationships than unknowns. And what that means is there's going to be an infinite number of triangles that represents that has those bits of information, right? If I give you too many, right, there's going to be no solutions and so on, right? So I want to give you the perfect amount of information, okay, for you to be able to solve these problems, right? So we need 6 pieces of information, basically, right? Because we have 6 unknowns. So let's see, what pieces of information do we know? We just learned the law of sines. So that's sine of alpha over A equals sine of beta over B. We have sine of beta over B equals sine of gamma over C, right? I'm choosing these 2. I'm not gonna, well, okay, let me say it like this. We also have, of course, sine of alpha over A equals sine of gamma over C, but that's not a separate equation, right? That one is equivalent to these 2. That one comes from these 2. So that's not a real equation, all right? But these first 2 are real equations in that they are independent from each other, right? Knowing the first guy, we actually had to give us a separate argument for why the second guy was true, right? So these 2 guys are independent equations, whereas the third guy comes from the first 2, so that doesn't really count, okay? So we have two relationships between our variables, right? So each of these you can think of as a relationship relating the variables. So, sine of alpha over A equals sine of beta over B relates alpha, A, beta, and B. Okay? And same thing with the second one. All right, what else do we know? We know this is a triangle, and so we actually know that alpha plus beta plus gamma is equal to pi, or we're using degrees in this section, so 180 degrees. All right, so we actually have, just knowing that we're working with a triangle, right? Just from the fact that we have a physical triangle, we have three relationships. This one here, and this one here, that are always true. Okay? What does that mean? Well, that means that if we want to kind of have a problem that has a finite number of solutions, we need to, we have 6 unknowns and 3 equations. So we need 3 more, either 3 more equations or just 3 more pieces of information about our unknowns, right? So we have 6, we have 3, we need 3 more. And so that's where our idea of solving the triangles comes in, where we give you the other 3, right? We literally tell you what the other 3 is, right? So like we said, maybe I tell you A is equal to 3, B is equal to 7, alpha is equal to 10. 10 degrees, right? So I'm literally going to give you 3 more pieces of information in that I'm literally going to tell you what those qualities or what those values actually are, all right? And if I do that, right, if I tell you A is equal to 10, B is equal to 7, alpha is equal to 5 degrees or something like that, how many pieces of information will I have in total? 1, 2, 3, 4, 5, 6. Okay, so what I expect that in general is that there will be a finite number of triangles that represents these 3 pieces of information here. Okay. All right. If I omit one of these, if I omit alpha equals 5 degrees, I will only have 5 pieces of information. And so then there'll be an infinite number of triangles that have A equals 10 and B equals 7, right? And of course, we don't, really want to talk about a situation where we have an infinite number of solutions, too many. All right. Let's see. If I, let me also say this. If I give you too many bits of information, so let's say I say we have alpha is 10, A is 10, B equals 7, and let's say I also say, alpha equals 5 degrees, and I also say C equals 15, right? That's going to be 7 pieces of information, our 3 from above, and then 4 more. So generically what that means is that there is no triangle that has A equals 10, B equals 7, 5 degrees as alpha, and C equals 15. All right. So if I give you too many pieces of information in terms of the alpha, betas, and gammas, generically there will be no solutions to the problem. There will be no triangles representing these 4 bits of information. All right. So you'll notice one of the problems in the online homework, they give you actually 4 pieces of information. And what that means is your first thought when you see that on the online homework is that there are 0 triangles that represents those 4 pieces of information, or that there's 0 triangles that have those 4 pieces of information as their side lengths or angles. And that happens to be the case in that problem. Again, I want to stress generically, right? Because occasionally, by luck, it might work out, but generically it won't, right? Maybe you can think of it this way. When I say generically, one way you can think of it is if you just randomly choose 4 quantities, right? A equals 10, B equals 7, alpha equals 5 degrees, C equals 15, then there's not going to generically, if you randomly pick, there's no chance that it'll actually represent a real triangle, okay, probabilistically. Actually, if you do take, study some probability, there's literally 0 probability in that situation. All right, So 3 pieces of information is the perfect balance, right? If I only give you like I said, 2 pieces of information, there'll be an infinite number of triangles. So this is the perfect middle ground where we have 3 bits of information, 3 equations, and so all together we can solve problems that have 6 unknowns, which is literally what we have, right? We have 6 pieces of information that goes into a triangle. All right, so now that we kind of understand why all the problems in this section and 5.2 are the same, right? They're all, I give you 3 bits of information and you tell me what triangle this is, right? Let's actually start to think about how to actually solve these things. So the first thing I'm going to do is just write out what all the possibilities are in terms of the information that you could be given, right? 3 bits of information. So we have sides and angles, right? So if I'm going to give you 3 bits of information, it could be 3 sides. It could be, so let me call it side, 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 right? I could give you 2 sides and an angle, right? And there's 2 ways to do this. 2 sides and an angle. It could be, the first 2 sides and then the third one is an angle. And when I say this, I mean this in terms of what you learned when you first learned triangles, right? The kind of most basic version of trig, where SSA means you have a side and then you have a side adjacent to that one and then an angle adjacent to that guy. Okay, so this SSA having these 3 bits of information means I know this side right here, I know that side right there, and I know that angle right there. Okay. All right. So most importantly, it's 2 adjacent sides and then an angle next to the the second side. All right. Okay. What else? We have side, angle, side. Right. So that one's actually very, very different because that represents knowing this side, the angle in between the sides, and then the next side. All right. Very, very different. So even though both of these represent knowing 2 sides and an angle, they behave very, very differently. And we'll see that today, actually, because the SAS version we're not going to be able to deal with today. All right, let's see. We have angle, side, side, right? That would represent a picture like this, angle, side, side, right? But actually, for the purposes of our class, for the purposes of 5.1 or solving triangles, we only actually care about the relationships between, as in what is next to what, right? Here, the first one, we have a side next to a side next to an angle. The second one is a side next to an angle next to a side. And the third one is angle next to side, side. But that's the same as side next to angle, just reading it backwards. Okay, so for our class, ultimately, in terms of solving triangles, this SSA here is going to be the same as the ASS here, all right? So I'm going to be writing down a whole bunch of these, but a lot of them are actually the same. So it's not as intimidating as it might look. Okay, so these second 3 are all the ones which have 1 angle and 2 sides, where I give you 1 angle and I give you 2 sides, and you have to solve the triangle, right? The next bunch is where I give you, so here, first one was no angles. The next 3 were 1 angle. So the next ones are 2 angles. So if I give you 2 angles, there's 3 possibilities. I could give you a side and then 2 angles next to that side, right? So that would be the picture where I give you this side and then this angle and then that angle right next to it, right? I could give you a side, an angle, a side, and an angle, right? Like that. So that would be the picture where I give you this angle, this side, and that angle. Again, very, very different from the previous one because here the side is in between the 2 angles. And the one above, the side is not in between the two angles. Makes a huge difference for us. Okay, and the last one is where I give you 2 angles and then a side. And again, for the purposes of what we're doing, these 2 are actually, this one and the one up here, SAA and AAS, are actually going to behave the same for our class. All right. So those were the next 3. And then finally, there's one where there's a situation where I give you 0 sides, right? Or 3 angles, right? 0 angles, 1 angle, 2 angles, and then 3 angles, AAA. There's only one possibility there where I give you, again, all three angles, okay? So these are all the possibilities for the kinds of information I can give you um, and reasonably ask for you to figure out what triangle represents those three pieces of information. Or another way to say it, what triangle has those given three sides and lengths. Okay? All right. So for example, again, for the first one, I would give you A equals 10, B equals 7, C equals 15, for example, right? And I would ask you, what triangle has that A, that B, and that C, right? What are the alpha, betas, and gammas? Okay, before we begin, let's actually throw away one of these. So this last one, AAA, that one's no good because that's actually not 6 pieces of information if I give you AAA. Because what happens is we had 3 pieces of information from our law of sines, 2 law of sines, right? And we had the fact that alpha plus beta plus gamma is 180 degrees. So what happens is if I give you AAA, that's actually only 5 pieces of information because if I tell you the first angle is 30 degrees, and let's say I told you the second angle is 20 degrees, then me telling you this last angle is not new information because I already know the last angle from alpha plus beta plus gamma is 180 degrees, right? I already know that the last angle has to be 130 degrees, right? So how many pieces of information did you actually give me when you told me AAA was 30, 20, 130? You only gave me 2 bits of information, right? You only gave me, for example, this one and this one. Because the third one I already knew from the 180 degree property of triangles, right? So this AAA combined with the 3 above looks like it's 6 pieces of information, but it's actually only 5. And so what that means is there's actually probably going to be an infinite number of triangles with angles 30 degrees, 20 degrees, and 130 degrees. All right. And in fact, there are, because if you think about the basic trig that you probably learned, you know that about similar triangles, right? We talked a little bit about it in Math 92. And we know that, given any 3 angles, you can have this triangle with those 3 angles, but I can always stretch that triangle or expand that triangle or shrink that triangle to get another one with the same angles, right? But different lengths. All right. So we know actually for a fact that giving AAA leads to an infinite number of possibilities. All right. Potentially it leads to an infinite number of possibilities. There could be 0, of course, right? If I give you AAA was 30, 20, and 10, they're not even going to add up to 180 degrees. So that obviously wouldn't work. Okay. All right. So AAA, you'll never see any problems in 5.1 or 5.2 regarding AAA because, there's an infinite number of solutions. All right. So that's not what we're kind of focused on problems where there's a finite number of solutions or no solutions, of course, right? That can always happen as a possibility. All right. So that means our 8 potential problems actually turns out to be only 7. Like I said, it'll turn out, and we'll see this very soon, that SSA and ASS are actually the same. And SAA and AAS and actually ASA are all the same. So there's much fewer problems than it seems like, or kinds of problems than it seems like there might be. All right. Okay, actually, let me talk about that latter point right here. So SAA, ASA, AAS, why are these guys all the same? Well, all of these guys, I'm giving you 2 angles, right? 2 angles, 2 angles. But because I know triangles, the angles have to sum up to 180 degrees. If I give you 2 angles, automatically that means you know the third angle, right? Again, if I told you one angle was 59 degrees, the other angle was 61 degrees, then altogether we have 120 degrees. So that means the last one is 60 degrees, right? It has to be 60 degrees. So giving two angles automatically gives me the third angle, right? And so if you think about this, right, here's the picture for SAA was SAA was this one, ASA was this one, AAS is this one, right? But again, if I know these two angles, then automatically I know that third one. If I know these two angles, automatically I know this third one. If I know these two angles, I automatically know this third one, right? So if you look at all these pictures, they're all the same in a way, in that I know all three angles and one of the sides. All three angles, one of the sides, all three angles, one of the sides. All right. So these three are all going to behave exactly the same. All right. So when you see a problem where they give you two angles and a third side and a side, it doesn't actually matter which side it is, because you automatically get, your first step is to figure out the third angle, right? And then you're in a situation where you know three angles and a side, and then we'll see how you deal with that in just a couple seconds. All right. So these three actually behave exactly the same. All right. So let me write it like this. Same in quotes. All right. And again, these two will behave exactly the same. We'll see in just a second. And so ultimately, in a way, there's really only 1, 2, 3, 4 different kinds of problems of this kind. All right. So from a potential 8, there's really only 4. So what might look initially overwhelming, for these sections, is actually not as bad as it might seem. Okay, so let's actually solve some triangles. All right, the way I'm going to do it is going to be different from the book. So I really, really hate how the book does it. Does 5.1 and 5.2 in terms of solving triangles, because they kind of, if you even look in the book, they give you an algorithm. Step 1, do this. Step 2, do this. If it's SSS, do this. If it's SAA, do this. If it's SAS, do this. And each of those do this parts is going to have steps, right? If it's SAS, step 1 is this. Step 2 is this. Step 3 is this. If it's SAA, step 1 is this. Step 2 is this. Step 3 is this. Because all of them are going to be different. So if you kind of try to do the problems that way, first of all, it's a huge kind of, it's a whole page in a way of algorithm, because there's so many different possibilities. And second, you're not going to be able to remember all that, in practice, right? Let's say on an exam, right? How are you going to remember a whole page's worth of algorithms, right? So it's terrible. And also, the kicker is he also uses some facts that we technically don't know, right? So he uses the fact that if we look at the law of cosine section, he uses the fact that the largest angle corresponds to the largest opposite side, right? Now that's definitely true, but we haven't justified it, and he doesn't, I don't believe he justifies it in the book. And again, I really hate that, right? Using things that are just in a way magic, that are unexplained. So for these reasons, I'm going to do it, explain this section differently, the solving triangles. But the way I'm going to explain it, I think hopefully makes more sense, or is easier to remember, because it's just going to involve writing down our laws and taking a look at which bits of information we have. And from there, it'll be pretty natural in terms of figuring out what bits of information we need to figure out. All right, so let's actually do this for a problem. And let me do an abstract version of this first before I do an example with numbers. All right, so let me deal with the 3 chunk here, SAA, ASA, AAS, right? So SAA / ASA / AAS. And again, one thing I want to emphasize here, you don't have to memorize that these are the 3, because again, the way I'm going to do these, it'll very naturally pop out what you need to do. All right, so you don't have to do any really much memorization at all. Okay, if any. Oh, by the way, for these problems, obviously, when we do the ones with the actual numbers, we're going to need a calculator, because we have the sine of alpha, sine of betas and stuff, and we're going to need to figure out alpha and beta. And how do we do that? We're going to need a calculator to do some arc sines. All right. Okay, so this is one section where, generally I try to discourage the use of calculators as much as possible, but here you're going to need to use a calculator. But I still would encourage you to use calculators as late as possible in a problem, because again, every time you use a calculator, you introduce a small mistake to your computations, and they can add up. And actually, that does happen in the problems here, where for example, if the book asks for 2 digits in their online homework, if you're not keeping enough digits, you're going to get the wrong answer by a decimal point. And then obviously the online solution is going to be wrong by 1 decimal point, and then it's going to be really frustrating. So one thing to do when you do use a calculator, keep 4 or 5 decimal points, just to make sure you're not kind of getting mistakes because of the calculator. All right, so let's do this. Let me do an example like this. So alpha, beta, gamma, C, A, B. And again, I'm going to do this abstractly first, and then I'm going to do a numerical example. So let's say I give you 3 bits of information. I'm giving you 2 angles and a side, right? So, sorry, maybe I should have done the other one first. Let me think about this for 1 second here. Yeah, I think we're okay. We're okay. All right. I do want to start with this one. So 2 angles and a side. So let's say I know this angle, I know that angle, right? So for example, alpha equals 30 degrees, gamma equals 20 degrees. Again, like I said, automatically. So I'm going to circle the ones that we, so the red ones are the ones we were given, and we're given a side. Before I even kind of circle the side, it doesn't matter, right? Because I already know beta, right? From the 180 degrees. So if I give you alpha and gamma, automatically we know beta, because sum of angles is 180 degrees. Now let's say I also gave you a side, B, right? Then what I do is I write down the law of sines. Sine of alpha over A equals sine of beta over B equals sine of gamma over C. Okay. Now what I'm going to do is I'm just going to circle the bits of information that I know, right? I know B, I know alpha, so I know sine alpha, all right? Using a calculator, for example. I know beta, so I know sine beta. I know gamma, so I know sine gamma, right? So the only thing that I don't know are A and B, okay? Or sorry, A and C. All right, but if I look at all the things that I circled, it's everything that I circled is a number, right? That we can just compute, right? Either by hand or using a calculator. And so if I look at this, let's say, so what I would need in this situation is A, right? But look at this, sine of alpha is circled, so it's a number that I know. Sine of beta and sine of B are circled, so those are numbers that I know, right? And so ultimately what that means is, let me write those two just by themselves. Sine of alpha over A equals sine of beta over B. I know this whole right-hand side. I know that guy. And so ultimately, that means A is equal to B over sine beta times sine alpha, right? And again, I know sine alpha, I know B, I know sine beta. So automatically, that means I know A. All right? And C, literally the same, right? Again, I know sine beta and I know B. I know sine gamma, so I know I can solve for C, right? So in fact, let me kind of write out the same things. Sine gamma over C. I know this guy, I know that guy, I know that guy, right? And so that means I can solve for C. C is equal to B over sine beta sine gamma, right? And let me emphasize again, I know B, I know beta, I know gamma. So that means I know C. All right. So these problems are actually very straightforward. This SAAS situation is very straightforward, right? Circle the guys that you know, and it'll be immediately obvious how to solve for the other guys. All right, so let me give you a kind of a numerical example. So maybe let's say alpha equals 20 degrees, beta equals 35 degrees, and A is equal to 10, right? So in this picture, we would have alpha, beta, gamma, A, B, C. We would know alpha, we would know beta, and we would know A to start with, right? But again, because the sum of the angles is has to be 180 degrees, right? Gamma has to be, let me write out the problem name. So find, let me just write solve the triangle. And in other words, find gamma, B, and C. All right. Okay, so gamma is equal to 180 degrees minus alpha minus beta, which is 180 degrees minus 20 degrees minus 35 degrees, right? And here I just have to do some arithmetic. I guess this is 160 degrees minus 35 degrees, which is going to be 125 degrees. Done, right? Done with our gamma. All right, so we've got our gamma. Now, now let's actually start to use some technology, the law of sines. Law of sines tells me sine of alpha over A equals sine of beta over B equals sine of gamma over C. All right, and again, what do we know? We know A, we know alpha, we know beta, we know, at this point, we know gamma, right? And so let me just fill in the stuff we know. Sine of alpha is sine of 20 degrees, right? A, we're literally told is 10. Sine of beta is sine of 35 degrees over B, which we don't know yet. And then sine of gamma, we just figured out that gamma was 125 degrees over C, right? And here you can literally see this guy on the left is just a number, right? You can plug that into a calculator. Sine 35 degrees, just a number. Sine 125 degrees, just a number, right? And so B is equal to, using the left, using this equality right there, B is equal to 10 over sine 20 degrees times sine 35 degrees, right? And using the same thing, C is equal to 10 over 20, sine 20 degrees times sine of 125 degrees, all right? So for the C, to get C, we're using the equality where this, maybe I use a different color, where this guy is equal to that guy. Okay. Notice, once I figured out B, I can use the sine 35 degrees over B to get C, but it's better to use the first one. Because first of all, you did 10 over sine 20 degrees with a calculator already, right? And these two are the same, so you don't have to do the same computation twice. And second of all, getting B will have some error, right? Because you use a calculator to get B. And then when you use the same, that flawed value to get C, you're introducing more errors into your problem. Okay. All right, that's a minor point, but again, it might cause you a little bit of problems in the online homework. Okay, but ultimately, right, these are just numbers, and I can plug them into a calculator, and that's what you should be doing. At this point, you're going to have to plug into a calculator in the online homework, all right? And if I did do that, right, I would end up with, this is going to be roughly, I said don't use equal signs, right, when things are not equal. So roughly 16.77 degrees. 16.77 length is 16.77 and 23.95. All right. One thing, when you do plug into a calculator, make sure you're using degrees, because all of these guys are given in terms of degrees. All right. So switch from radians to degrees if your calculator defaults to radians. All right. So that's it, right? Let's see. So we have our final conclusion. Gamma was 125 degrees. B was roughly 16.77. C was roughly 23.95. And we were given A, B, alpha, beta, and A. So altogether, we have all 6 bits of information that our triangle represents. And so we've solved the triangle. Okay, so seemingly pretty straightforward. All right. let's take a look all the way up here again. So we have now completely resolved these three guys. We're not talking about the AAA, as we said. Now let me say a few words about the other four. So SSS we're not going to deal with today. And SAS we're not going to deal with today. We'll talk about why we're not going to deal with them after I talk about the other two. So the other two, what we're going to talk about now is SSA and ASS. All right. So more importantly, it's the ones where you have two consecutive sides and then an angle. All right. So let's talk about the SSA/ASS situation. And again, you don't have to memorize, which situations are which, because what we're going to be doing is we're going to write down the law of sines and then figure out what we should do from there. All right. Let me do this with an example. So this one is actually going to be the complicated situation, which can have a lot of possibilities. So let's solve triangle where alpha is 25 degrees, A is equal to 20, and B is equal to 40. All right. So if I draw the picture here, alpha, beta, gamma, A, B, C. In this situation, we know this one, we know that one, and we know that one. All right. So an angle and two consecutive sides. All right. And importantly, right, the angle is not between the two sides. That's a different situation. Okay. Here, we can't start out with the 180 degrees that we did before because we only know one of the angles, right? So the other two angles, there's no way we can get them. Last time, in our previous example, we knew two of the angles, so obviously we could get the third, right? But now we only know one angle, so we can't do that, right? So that already you can see that this one is not as straightforward. Okay, let me write down the law of sines. Sine of alpha over A equals sine of beta over B equals sine of gamma over C. All right, let's circle what we know. We know B, we know alpha, and we know A. All right. Okay, so the important thing to notice is we know this entire quantity here. All right, that one is a number, right? Sine alpha is sine of 25 degrees, and A is 20, right? So let me actually fill in the numbers just to emphasize that heavily. So this is sine of 25 degrees over 20 equals sine of beta over 40 equals sine of gamma over C, right? And here you can see we don't know anything about this last equality, right? Whereas we know this number, we know that number, and we don't know that number. Okay, so just circling what we know, we can see we can solve for sine beta, right? So sine beta is equal to 40 times sine 25 degrees over 20, right? Which happens to be 2 sine of 25 degrees. All right, so we actually know sine beta. So sine beta is equal to this number. And so I actually know beta, right? So beta is equal to, well, here's what I'm going to do. I'm going to plug into the calculator. I'm going to use the arcsine button of the calculator and calculate arcsine of this quantity here, 2 sine 25 degrees, right? And my calculator is going to give me a number. So calculator, use calculator. And what I'm going to get in this example is the calculator is going to give me roughly 57.697 degrees. Okay. All right. Here's where we have to be careful. So we use the calculator to get this arcsine, but when we use the arcsine button in the calculator, or when we talk about the arcsine quantity, when we talked about inverse trig functions, we know that arcsine only gives you angles between minus pi over 2 and pi over 2, right? However, there's the possibility that there's another angle where sine of that angle is 2 times sine of 25 degrees also, right? And you can see that in the picture. So here's sine between 0 and 180 degrees, right? I only care about, so we're working with triangles, right? And triangles only have positive angles. So I'm not even going to bother drawing sine on the left side here, right? Triangles have angles that add up to 180 degrees. So I obviously can't have any angles bigger than 180 degrees, so I'm not even going to bother to draw sine out here. Okay, I only care about angles between 0 and 180 degrees for this type of problem. All right, now take a look at what our calculator told us. Our calculator told us beta is 57.697 degrees. So that's going to be, let me label this here. This is 90 degrees right here, right? 57.697 lives somewhere, let's say like right there. All right, 57.697. Okay, now what we've done with the calculator is we've discovered that sine of this number, 57.697, is that guy right there. And what is that number? That number is 2 sine 25 degrees. Right? However, if we look at this, there's another angle right there that also gives that sine of that angle is also the same number, 2 sine 25 degrees, right? So this guy right here, let me do it in red. This guy right there, that angle right there, sine of that angle is also 2 times sine 25 degrees, all right? So what we had was, we knew that sine of beta had to be this number, 2 sine 25 degrees, right? But there's actually two angles whose sines are that number. So they're actually potentially, at this point, we know there's potentially two triangles that have the sides and angles that we were given, all right? So this guy right there, what is that? Well, this is where the solving of the sine and cosine equations come in, right? If I look at this guy right there is 57.697, right? Then that guy right there, so that 57.697 represents this length right there, okay? So that, because of the symmetry of sine, that's the same as this length right there, right? So the point that we're looking at right there, the angle that we want is 180 degrees minus 57.697 degrees. All right. So that's actually a second possibility for beta. All right. So in this problem, there's two possibilities for beta, 59.697 and this other one, which happens to be, if I just do the subtraction, 0.303 degrees. All right. So there's two possibilities, two possible betas. All right, 57, so beta equals 57 or let me again say roughly 57.697 degrees. And again, I always want to put the degree symbol. And beta 122.303 degrees. All right. So it's really important to remember that our calculators will only give us one of them. There's potentially another one, all right? Because our calculator, the arcsine button, only gives you one possibility, right? It's always going to be missing all the other solutions when you're solving a sine problem, okay? All right, so how do we proceed? Well, we just separate this into two problems, right? Problem number one is we treat beta as 57.697. Problem number two, we treat beta as 122.303, and we solve them individually, all right? And whatever we get, right, potentially we could have two triangles as our answers, okay? All right, I say potentially because we'll see situations where triangles might not work out. All right. Okay, so good news. We've just done the difficult part because what situation are we in now? We now have beta, right? So let's scroll up and look at what we were given. We were given alpha, B, and A, and we just figured out that beta right there, right? So basically, if you think about this, we're in a situation very much like the first set of examples, the one where we were given two angles, right? If we have the beta, then that means we have gamma, right? Automatically, because 180 minus alpha minus beta has to be gamma. Okay, so automatically we have gamma. So this tells me gamma is equal to 180 minus alpha minus beta, right? Which is 180 degrees minus alpha was, I forgot already, 25 degrees, right? And beta in this side of the board, or in this side of the screen, it's 57.697 degrees. Okay. All right. If we compute that, that's going to be, or I guess I should use squiggly lines. So equals here, and I should use squiggly lines here because our beta is not exactly 57.697. So our gamma is not exactly 180 minus 25 minus 57.697. So this is squiggly lines, approximately 97.303 degrees. All right. Okay, so at this point, we have alpha, beta, and gamma, right? So let me scroll back up again. So we have alpha, beta, and gamma. So the only thing left that's not circled is C, right? But if we look at our law of sines again, let me use a different color here. If we look at our law of sines again right there, right? Let's update which information we know. We now know sine of beta because we know beta. We now know sine of gamma because we know gamma. So the only thing that's not circled is C, so we can solve for C, right? In particular, what I'm going to use is I'm going to use the sine 25 degrees over 20 and the sine of gamma to find C. All right, so let me copy down the first and last parts there. So sine of 25 degrees over, sorry, I forgot what it was already, 20 is equal to sine of gamma, which is 97.303 degrees, over C. All right. And again, technically, I guess I should use squiggly lines here. All right. Because gamma is not exactly 97.303. All right. Once I've used a calculator, then you know, they're small. Nothing is equal, right? They're approximately. Okay, but the point here is this left-hand side, I know it all. The right-hand side, I know everything except C. And so C is approximately sine of 25 degrees over 20 times, divided by, so let me write it like this, divided by sine, or sorry, let me write it just as 1 over sine of 97.303 degrees. Okay. And this guy, I can just put it in the calculator. And if I do that, I'm going to get 46.94, roughly. All right. And that's it, right? Let's see. We've got C is this. We've got beta is this, right? And we have gamma was this, right? So those were the three that we were looking for. Okay. So we've solved the left-hand side of the problem, right? So we've actually discovered a triangle that has alpha equals 25 degrees, A equals 20 degrees, and B equals 40 degrees. All right. Now, the other side of the board, we're still going to do. So this particular problem, we're going to end up having actually two triangles, two possible triangles. All right. Notice one thing I want to emphasize here. When I solve for C, right there, when I solve for C, I used the sine 25 degrees over 20 instead of the sine beta over 40, which I could have used because I know beta, right? At this point of the problem, I know beta. But I want to use the sine 25 degrees over 20 because those guys, 25 degrees and 20, were given to me precisely, right, as alpha equals 25 degrees, A equals 20 degrees, right? Whereas the sine beta, I only have it approximately, right? So there's less chance of having errors if I use the quantities that I know precisely as opposed to quantity I know only imprecisely, the sine beta, okay? Obviously, if we have no choice, we have to use it. But in this case, we have a choice. And I choose to use the one where I have more precise information. Okay. All right. So again, the kind of idea here is, at least for this section 5.1, just write down the law of sines, circle the quantities that you know, and then it'll be very frequently obvious which ones you can get from that. And then every time you get one, circle that one, and then look at which ones you can get from that, and so on. All right? Okay, so for the other side of the board, the idea is actually the same, right? The process is literally the same because for the other side of the board here, we have beta is 122.303 instead of 57.697. But still, the process is the same because at this point, if we have beta and we were given alpha, then we know gamma again. Gamma is 180 minus alpha minus beta, which in this case is 180 minus 25 degrees minus the beta from this side of the board, 122.303, right? And if I actually subtract that, I'm going to get 32.697. Okay. Oh, by the way, in terms of notation, I don't have to use the squiggly lines here. I can use the equals there because gamma is equal to this, is squiggly that, and that is equal to this. But altogether, gamma, because of the squiggly line in the middle step, gamma is roughly equal to that. Okay? That's just a small notational detail. Don't worry too much about it. Okay, so I know gamma, right? So now I know gamma. I know beta, right? And then again, I scroll up and then I see that I have this sine 25. I now have the 20. I have gamma, so I have sine gamma, and so I can solve for C. So it's literally the same process, but with different numbers, right? With our second option, second possible beta. So this is sine of 32.697 degrees over C. And so C, again, this probably should be a squiggly here. C is roughly sine 25 degrees over 20, 1 over sine 32.697 degrees. Okay, and the reason I wrote the 1 over instead of dividing is because if you have a more fancy calculator, you can save this quantity and use it again here, right? Okay, so you ultimately end up with 25.567 if you plug that all into, oh, sorry, not degrees, if you plug it all into a calculator. Okay, so this particular problem has two triangles, so two solutions. Beta approximately 57.697, gamma approximately 97.303, and C approximately 46.94. All right. And then on the other side, we have beta is approximately 122.303. Gamma is approximately 32.697. And C is approximately 25.567. All right, and again, when you use your calculator for these problems, probably it's a good idea to keep 3 to 4 digits, just to make sure you're when the online solution is checking your answer, that you'll have less chance of having a error. Okay, so what this means is that there's two possible triangles. So two, let me write it like this: two possible triangles, two triangles that have A equals, sorry, let me A equals 20. I think I wrote alpha first. Alpha equals 25 degrees. A equals 20. B equals 40. All right. That's strange, right? Why 2? I'm going to draw a picture at the end explaining why. Why some of these problems will have one triangle, why some of them have 2, why some of them will have none. All right. All right, but for now, everything fits algebraically, and you just follow the algebra. All right. If the algebra tells you there's 2 solutions, then there's 2 solutions. If the algebra tells you there's 1, then there's 1. Okay. All right, let me do another example. Again, we need to do a few examples here because there's a few situations for this case. Alpha equals 25 degrees, A equals 10. So starting out, it looks the same, right? But B equals 42. Okay. So notice our previous problem was same alpha, same, sorry, I guess we're not using the same A. All right, so not as similar as I thought. Maybe I should have done the same and just changed B, but I didn't. Okay, but in any case, it's the same concept. We have alpha, A, and B, right? So alpha, beta, gamma, A, B, C. What do we know? We know alpha, we know A, and we know B, right? So again, we have 2 consecutive sides in an angle, right? So it's the same situation, of course. All right. So again, let's write down our law of sines. Alpha over A, sine beta over B, sine gamma over C. Circle the guys we know. That guy, that guy, that guy. All right. And again, just from looking at the circle, at which guys are circled, immediately we feel like we should solve for beta, right? Because if we look at the first equation here, everything is known except for that beta. So we should solve for beta. All right, so let me do that. So sine of beta is equal to B times sine of alpha over A, right? Which is going to be, let's see, B was 42, A was 10, sine of alpha is sine of 25 degrees. All right. Okay, let me calculate that. So now I'm going to use a calculator to calculate the sine 25 degrees. And this turns out to be, and then times 42 over 10. That turns out to be 1.775 degrees. Okay. Sorry, not degrees. 1.775. All right. It's not degrees because it's not representing an angle. All right, because it's representing the sine of something, which are not angles. Okay, now, what does this mean? Well, sine of beta should be equal to 1.775, right? That's what our equation has told us. But we can't have that, right? Sine of anything is always less than 1 and bigger than minus 1, right? So there's no angle you can put into sine to pop out 1.775. And so that means there's no solutions. Right? And if you did plug this into a calculator, right, to calculate the arc sine of B, to calculate beta, right, as the arc sine of 1.775, it'll give you an error because there is no arc sine of 1.775, right? Because the domain of arc sine is between minus 1 and 1. So there's no solutions. So this means that there's no triangles. So no triangles, let me write, there are no triangles that have sides that have one angle equals 25 degrees, and then 2 consecutive sides being 10 and 42. All right. Okay, so I've said, when you have 6 bits of information, you generally have a finite number of solutions, but this is where that phrase generally comes in. Sometimes there are no solutions, all right? Depending on your specific setup. Okay, let's do another example. And this is going to be the third situation that can happen in these type of problems. So solve the triangle. Beta equals 20 degrees, A equals 5, that's a beta right there, and B equals 8. All right. Okay, let me draw a picture. Alpha, beta, gamma, A, B, C. What do we know? We know this guy, we know that guy, and we know that guy. So again, it's a situation, one angle and then two consecutive sides. Or two consecutive sides and then an angle. Again, it doesn't matter which way we read it. Okay, again, because we only have one angle, we cannot figure out the other two angles yet. So our only other option is to consider the law of sines. All right, and then for law of sines, let's circle which ones we know. We know that. We know A. We know B. All right, so this is a situation where we know this middle guy completely, right? Sine beta over B. And we don't know the sine gamma over C. We don't know any of those guys, either of those guys. So we don't want to work with that one immediately because it has two unknowns, right? We'd rather work with the terms that have fewer unknowns. So that would be the sine of alpha. So that's my justification for working with the sine of alpha over A, and then later dealing with the sine gamma over C. All right. So I'm working with the sine alpha over A equals sine beta over B. And again, just to emphasize, I know that, I know that, I know that. And that would be sine alpha over A was 5. Sine beta is sine of 20 degrees. And B is 8. All right. And so sine of alpha is 5 over 8 sine of 20 degrees. Okay. All right. So now I plug it into the calculator. So alpha is equal to arc sine 5 over 8 sine of 20 degrees, right? We plug that into a calculator and we're going to get something like 12.343 degrees. Okay. All right. Again, when we use arc sine, we're not, so I guess maybe let me phrase it like this. We actually want to solve this equation, right? And we know there's an infinite number of solutions. We only want the solutions between 0 and 180 degrees. So there's only going to be at most 2 solutions, right? When we use arc sine, we only get one of them. For sure, we can only get one of them. So we always, always, always have to check if there's another one, all right? Because we're not really, here alpha equal, when I write alpha equals arc sine blah, 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 that's only one possibility, right? The actual solution, actual problem we want to solve is this one, which has multiple solutions. Okay. All right. Let me draw a picture again, just to emphasize why there's 2 solutions. So here's 180 degrees, here's 90 degrees, here's 12 point, sorry, there's not enough space there. 12.323 degrees. We can see that we wanted the output right there, right? That height, this height here represents 5 over 8. 5, here we go. 5 over 8 sine 20 degrees, right? That's what this height here represents. And we wanted an input for sine that gives that as an output. Our calculator gave us this one right here, 12.323 degrees, but there is another one, and we can literally see it right there, right? And so the other possible solution, or the other angle that we're looking for, lives right there, 180 degrees minus 12.323 degrees. Okay? So we always want to keep in mind there's another possibility. So also, let me write it down here. Also, alpha equals 180 degrees, or let me put squigglies, minus 12.323, right? And that happens to be 167.657 degrees. Okay, so from here, we do the same as what we did last time. We have two possible alphas. So alpha is equal to 12.343. We have alpha equals 167.657, or maybe I should use squigglies for both of these, approximately, right? And we solve them as individual problems. Okay. How do we solve the one on the left? And how do we solve the one on the right? Using the exact same procedure. Let me scroll up and circle the new information that we know. So now we know alpha, right? We have two possibilities, but we know alpha. So we know that guy. Okay. And let me circle it up here in the picture. We know that guy, right? But again, once we know two angles, we automatically know the third, right? So automatically now we know sine of gamma. And so C is the only thing left. How do we solve for C? Well, we throw the sine gamma to the other side and we've got C, right? And so again, just writing down the law of sines and circling the guys you know can lead you to the right process without having to memorize a whole bunch of algorithms. First step, do this. Second step, do this. Third step, do this, right? Just the only step is write down the law of sines, draw a picture of your triangles, circle the guys you know, and then work from there. Okay, so if we just continue in exactly the same way, our gamma is equal to 180 degrees minus alpha, so 112.343 degrees. And then minus, so this should be squigglies because we don't have it exact. And our B was 20 degrees, right? So this is equal to, if I just do the subtraction, nothing fancy going on here. This is 147.657 degrees. Okay, and again, now I know sine of beta over B equals sine of gamma over C. I know this, and now I know this. So that leads me to C, right? And again, let me emphasize, I know them as sine of 20 degrees over B was, let me scroll up. B was 8. So over 8 is equal to sine of 147.657 degrees over C, right? And again, technically I should use squiggly lines here. And so C is equal to sine of 147.657 degrees times 8 over sine of 20 degrees. All right. And I can plug that into a calculator, or I guess squiggly lines here. I can plug that into a calculator and get, again, our calculator is not exact, so another squiggly lines, 0.513 degree. Okay. And that's it, right? That's it for this side of the board. We have C, we have gamma, we have alpha, right? Those three go with the other three, B, beta, and alpha that were given. All right. So I have one triangle right there. And then now let's go to the other side. And here's where the other side is interesting. Our first step is, again, let's figure out gamma. Gamma is 180 degrees minus alpha, 167.657 degrees, minus beta, 20 degrees, right? Well, what do we get if we actually subtract these? We get minus 7.657 degrees. Okay. Problem, right? How can we have a negative angle? We're talking about actual physical triangles, and obviously a triangle can't have a negative angle. And so what that means is no solutions. No solutions to this side of the board, all right, or this side of the screen. Okay. And so we actually don't have to continue this problem, because this problem, if there was an alpha, if alpha were 167 degrees, then we would have a triangle that doesn't exist, that can't exist. Okay, so we just stop there. And so our problem has only one solution. It was, alpha was roughly 12.343. Gamma is roughly 147.657, and C is roughly 12.513. Sorry, I always put these degrees by accident here. No degrees there. C is just a length, so there's no degrees there. Okay, so we've seen that this setting where we're given two sides and two consecutive sides and an angle can have one solution, zero solutions, or two solutions. All right, and which one it is, you just work it out, and then you look at the math. Whatever the math tells you, it tells you. All right, so how could this be? What's the kind of reasoning for how this could happen? So here's a picture explanation. If I have two consecutive sides and an angle, let's say this side right there, this angle. So let's say I know that. Let me do it like this. So the things I know, this guy I know for a fact, this angle I know for a fact. All right, and then a third side, two consecutive sides. So let's say another side. All right, but this side right here, I actually don't know the angle that this side should make with that guy, with this second side. All right, so let's think about, I think I need to move this a little bit. Let's think about the possibilities. This side right here, it could be this angle. It could be this angle, right? It could be that angle, right? As long as it has the fixed length, right? Because we know that side, it could be any of those possibilities. So all the possibilities, if I draw them all together, they're going to form a circle, right? So for example, this is one possible side. That's one possible side, right? Again, I'm given, let me actually do some numbers. Let's say I'm given A equals 10, B equals 20, and C equals some angle, right? 30 degrees, right? Then I would know this is 30 degrees. I would know this is 20, and I would know that this is 10. But it could be this one, or it could be this one, or it could be this one, right? It could be any of those, right? Because all I know its length is 10. I don't know what angle it makes with the side of length 20, right? So this circle represents all the possibilities for this side right here, all right? Okay, now what happens is, let me draw the circle a little bigger just to emphasize what's going to be my point. So here's my circle. In other words, the vertex of my triangle could be anywhere on this circle, all right? Because anywhere on this circle, its distance to here is 10, okay? All right, now, what are the possibilities? Well, if I know this angle is 30 degrees, then this side right here has to be along this dotted line, right? It has to be along this dotted line, right? And so what happens is this dotted line intersects my circle right there and right there, right? What does that mean? That means there's actually two triangles that have angle 30 degrees, length 20 down here, and then side 10, because one of them is that one and the other one is that one, right? So one triangle, let me do them in different colors. One triangle is going to be this one, there, and there. The other triangle is going to be this one, there, and there. All right, so that's how it's possible to have two triangles. Okay. So again, in this situation, you're given this angle, that length, and then the length 10, which again, it could be multiple possibilities anywhere on this circle. But we've discovered that it's in this picture at least, it has to be this one, or it has to be this one, or else you're not going to form a triangle, right? Okay, now what about the situation where there's no triangles? Well, that's going to be something like this. Oops. Where you know this length, you know this angle, right? And you know, let's say you have to be on a circle there, right? So you know this length has to be a certain length, but again, you don't know where the side is, okay? You just know it has a length of this radius. Okay, now this one has no triangle corresponding to it, because if I were to extend this, it would never touch the circle, right? but we already know for a fact that the last vertex of my triangle has to live on this circle, right? So there's no triangle that can be created out of this, right? Out of this dotted line intersecting that circle, because they don't actually touch at all, right? Okay, again, a point of view is you're given this vertex, and that angle, right? And the question is, where's the last vertex? So in the first example, the last vertex could be here or it could be here. In this second example, where's the last vertex? Well, the last vertex has to be on the dotted line because we have to form this angle. But sorry, but the last vertex also has to be on this small circle. And since these two guys don't touch, no solutions. All right, so two solutions, no solutions. And then what about the one solution situation? Well, there's actually two possibilities. One possibility is something like this, where I know this length, I know this angle, right? Which again means my last question is, where is the last vertex? Now let's say, I think I need to move this again. I need more space. Okay, so the last one, let's say so again, we know an angle, we know a side, and we know a third side. So this side is represented by, let's say, a circle that looks like this. Let's say it's a really big side, right? Then the dotted line is only going to intersect the circle in one place, right? It actually intersects also down here, but we can't have that because we know the angle is in this direction, okay? And so the only possible triangle is the one that goes from here to here. All right, so there's only one solution here. Okay, right? In a way, this one here would be another solution, but it doesn't work because my triangle is going that way. All right, there's another one solution situation where the angle looks like this, and here's your dotted line, and the circle actually just touches the dotted line, right? Then there's only one possibility. All right, so in this situation, it's the dotted line is tangent to the circle. It's neither inside, the picture is neither inside, like this second example, or outside, like the first example, but it's kind of like an in-between, it just touches. So there's one solution here. All right, and this is an example where actually that's a right triangle. We know that, right? Remember we said way back in 1.5 that if you have a line that's tangent to a circle and then you look at a radius segment, then you form a right angle right there. Okay, so this is a right angle, right triangle. Okay, so that's the picture of what's going on with the three possibilities for side-side angle, or two consecutive sides and an angle. All right, finally, let me spend just a couple minutes talking about the last two situations, which were SSS and SAS. All right. Now, what happens if we try to solve these using our law of sines? So let me do SSS first. So SSS would be alpha, beta, gamma, A, B, C, right? So if we tried the same technique, alpha over A equals sine beta over B equals sine gamma over C, what do we know? We know that. So in the picture, we know this, and this. And immediately you can see we have a big difference between this problem and the ones we just looked at. The previous ones, notice that when we circle them, there was always one entire quantity that we knew, right? For example, we knew maybe sine alpha over A, both of those. Or we knew sine beta over B, both of those. But here, the ones we know are distributed in a way that we actually don't know any one of the sides. Okay, that's a huge problem, right? So for example, let's say I gave you A equals 10, B equals 8, C equals 5, right? Then what would we know? Sine alpha over 10 equals sine beta over 8 equals sine gamma over 5. So if we use two of these equations, what do we get? All we get is that sine alpha over sine beta is equal to, or sorry, let me just write it out first. Sine alpha over 10 equals sine beta over 8, right? We can't solve for sine beta because we have an alpha here, right? We can't solve for alpha because we have a beta here. In fact, you know, if you pick any of these equations, there's always two unknowns, right? So this is going to be much, much harder to deal with because we're solving for two unknowns here, right? So actually, it's going to be super, super, super hard, right? You have to solve these guys simultaneously. And so we're actually not going to do these, all right? So this is going to be 5.2. So the law of cosines, we'll deal with this easily. We'll deal with this easily. Okay, so while it's possible to do it, we're not going to do it using the law of sines, right? And again, you don't have to memorize that you need to use the law of sines for this, because if you just write down the law of cosines for this, because if you just write down the law of sines, it very quickly indicates to you that you're going to have some trouble here, right? You can't easily solve for any of the alpha, beta, gamma, because each of the equation, any equation that you write down is going to have two unknowns, right? So that indicates to you that it's going to be hard to do this with the law of sines. And so your thought process should be, maybe I should use the law of cosines, all right? And that's actually going to work. Okay, what about the other one, SAS? It's going to be a similar situation. If I know SAS, so let me again draw a triangle, alpha, beta, gamma, A, B, C. Then that means I know one side. So let's say this side right there, an angle, let's say that angle right there, and then another side, so that side. So this is important in that, important to note that the angle is between the two sides, all right? What that translates to in terms of the law of sines is sine of alpha over A, sine of beta over B, sine of gamma over C. Again, let me note, we only know one angle, so we can't figure out the other angles easily, right? If we knew two angles, we would get the third angle easily. That's always kind of our first thought. Our second thought is law of sines. Let's take a look at which ones we know. We know C, we know A, we know the sine of beta because we know beta. But again, we can't solve this one easily like we did the other problems, because if you pick any single kind of equation here, for example, the sine alpha over A equals sine beta over B, there'll be two unknowns, right? Alpha and B we don't know, right? And let me emphasize that by writing all three. Sine beta over B equals sine gamma over C, right? We don't know B or gamma, right? So there's two things we don't know. And the third one would be sine alpha over A equals sine gamma over C, right? Again, we know these two, but there's two we don't know, right? So this law of sines, which leads to these three, individual equations, don't help us very much, because all the individual equations have two quantities that we don't know, right? Two quantities we don't know. Two quantities we don't know. So it's going to be not so easy. Sorry, I think I circled the wrong ones here. Two quantities we don't know. So this was sine beta. This one. So the ones we didn't know were this one and this one. Okay, so in order to use the law of sines to solve this is going to be really hard, right? Again, let me contrast that. Let me scroll all the way up and contrast that with, for example, this problem that we did here, right? We knew sine beta over B, right? So we knew that entire side. And then we also knew, for example, A. So the sine alpha was easy to get. Okay, so these two SSS and SAS are not like that, right? When we circle the ones we know, we can see the ones that we don't know are really hard to figure out because every individual equation has two unknowns. Okay, so this one is going to be too hard for us, so we use the law of sines. A law of cosines. We'll make this easy. Really easy. Okay, so you don't want to use the law of sines for this. You could. It's actually possible to do it, but it's a huge pain. And why go through the huge pain when the law of cosines, which we'll talk about in 5.2, will get it to you very, very quickly and easily. All right. Okay, so again, you don't have to memorize that this one you have to use law of cosines. You just, naturally write down the law of sines and you'll see it's not going to be easy to work with. All right, finally, the last thing I want to talk about in this section is a revisiting of an application that we talked about a month ago or so, from 1.5, where we wanted to calculate the height of a tree, and we used trig to do it. We used right triangles to do it. But now we can do it using the law of sines. So let's revisit that problem, or a problem similar to it. Let's say we've got a tree, right? Some sort of tree like that. We've got, let's say, so this is a problem where, let's say we're viewing the tree from here, and we see that this angle is 20 degrees. Angle of elevation is 20 degrees, right? This was the problem where perhaps we have a river between us and the tree, or maybe we have, some rocks or something, some obstruction between us and the trees, maybe a river here. We can't actually figure out the distance from us to the base of the tree, all right? If we did, we would just do it very straightforwardly using this right triangle, all right? So instead, we walk forward a few steps, let's say 100 feet, and then we look at an angle of elevation again, right? And let's say this time the angle of elevation is, so here we've got rocks. So let's say this time the angle of elevation is 22 degrees, all right? So the question is, how high is the tree? Okay. So before, the way we did this was we considered two right triangles. So the big right triangle here, the tree and the ground. And then the small right triangle, the 22-degree angle, the tree and the ground. And then we did some kind of calculations using that, right? Now we're going to use the law of sines. So the way we're going to start is, I guess I should give a name here. The height of the tree, let's call this y. All right. Let's see. I'm going to look first at the inner right triangle. So I'm going to look at the inner right triangle. I'm going to call this hypotenuse right there. I'm going to call that capital Y. So let me call that capital Y. All right. Okay, so sine of 22 degrees is equal to opposite, which is little y, the thing that we actually want, over hypotenuse, which is capital Y. All right. Okay. Now, we don't know capital Y, but we recognize that if we can figure out capital Y, then we know little y, because then we just throw capital Y to the other side of the equation. All right. So what we're going to do is we're going to take a look at this other triangle right here. The triangle that goes from here to here, here to here, the two angles of elevations, and then this side 100. All right. I'm motivated to look at this triangle because, well, first of all, it has the side capital Y that I would like to find. Second of all, it has the side 100 that I know, and it has this angle 20 degrees that I know. And actually, it has a lot of other angles that I know, right? So this angle, this angle right there, because the other side is 22 degrees, that angle is 180 degrees minus 22 degrees, right? So that angle is actually going to be 158 degrees. All right. Okay, and in fact, of course, that also means I know this opposite angle if I wanted it, right? This opposite angle is going to be 2 degrees, right? It's going to be 180 minus 20, which is 160, minus 158. So that's going to be 2 degrees. Okay. All right. So in terms of the law of sines, right, this is a situation where I know all the angles and I know one side. So this is a situation where I can figure out, the rest of the sides, right? So if I just write down the law of sines here, involving the 20, the key point is involving the 100, right? Because that's the side that I know. Okay, so sine of 2 degrees over 100, right? So that's this angle right there over its opposite is equal to 20 degrees, sine of 20 degrees over capital Y, right? And I'm involving capital Y because that's the quantity that I would like to know, right? And so immediately I figured out that Y is equal to, capital Y is equal to 100 over sine of 2 degrees and then times sine of 20 degrees, just solving the algebra. All right. Okay, and now, because I know capital Y, that tells me little y is equal to, right, up here, right, little y is equal to y times sine 22 degrees. So little y is now equal to 100 over sine 2 degrees, sine 20 degrees, that's my capital Y, and then times another sine 22 degrees. Okay. All right, so we've gotten the height using the law of sines. All right, and one nice thing about actually this procedure here is that we don't need to take any arc sines or arc cosines or arc tangents or anything like that, right? We only need to understand how to calculate sines in order to write down this, in order to calculate little y here. So if in some situation we don't have a calculator to calculate arc sine, but we could figure out how to calculate sines, then we could still get little y using this technique. All right. Again, it's nothing absolutely new because we already knew how to do this problem using slightly different ideas, but it's a new viewpoint towards solving the same type of problem. Okay, so the next section is going to be 7.2.